My name is Srečko Glodež from the Faculty of Mechanical Engineering at the University of Slovenia, and today I will present the paper entitled Physical Analysis of Different Chiral Auxetic Cellular Structures. This research work has been done in the framework of the research program Design of Cellular Structures financed by Slovenian Research Agency, and the head of this program is Professor Ren. And here I also should mention the research project development and characterization of advanced metal materials for lightweight design. A few words about the cellular materials. So these materials are artificially engineered materials that possess some novel properties such as high stiffness to weight ratio, sometimes a negative Poisson ratio, then improved fracture resistance, improved specific energy absorption, and so on. These cellular materials may be used in different applications in the practice, such as lightweight design, then energy absorption, blast protection. Many different cellular structures are known or used in the practice, but we have oriented in our paper on the so-called auxetic cellular structures. What is important here? In the case on the compressive loading here on the left picture, we have actually contraction of cross-section. On the other side, on the right, in the case of tensile loading, we have expansion, and this is opposite if these auxetic structures are compared to the, let's say, classical structures. Many auxetic structures are known in the practice, but we have oriented in the chiral structures. What is chiral? This expression is known in chemistry. Namely, a molecule is called chiral if it cannot be superposed on its mirror image by any combination of rotations and translations. In our study, we have analyzed 5 different chiral structures, and the main goal of the study was first to obtain the auxetic behavior of these analyzed structures, and furthermore to obtain the fatigue behavior of these analyzed structures. As a base material, we choose aluminum alloy 5003, and we decided to use flat tensile specimens which was manufactured with water jet cutting technology from 4mm thick sheet. The quasi-static and fatigue testing, actually low cycle fatigue testing, was performed on the hydraulic testing machine Instron using appropriate extensometer, and all these experiments have been done at the Institute of Thermomechanics in Prague, because we had a bilateral project with this institute in the past. So in the case of the low cycle fatigue test, these tests were strain controlled, and amplitude strain range between 0.35% and 1.25% using strain ratio -1 and loading frequency 0.1 Hertz. Here you can see the results of quasi-static test. you can see three engineering curves and the averaged stress strain curve, which can be described with known Lampret-Osgood equation. And from this equation, the appropriate material parameters can be obtained, which were then used in the subsequent numerical or computational analysis. Here you can see the hysteresis loops of low cycle fatigue test for three different amplitude strain. It is evident that material hardening occurs for this alloy, and the stabilized hysteresis loop occurred, let's say, between 60 and 17% of the final fatigue life. So these results of the low cycle fatigue test can be presented with this Coffin-Mason diagram, for which the low cycle material parameters can be obtained, which can then be used for the computational determination of the fatigue life of the analyzed these chiral structures. And here is also the cyclic stress strain curve with the appropriate material parameters. These analyzed chiral structures were modeled in VBA script in the framework of the SolidWorks program package. Here is the computational model. At the top, we put the displacement, and here at the bottom, we have fixed restraints. The Poisson ratio can be obtained using these equations. It means the relationship between the strain in X and Y direction. And here on the right figure, we can see the results. It is clear that there is no auxetic effect by chiral structure and tetrachiral structure, but another three analyzed structures have this auxetic effect. In the case of the computational fatigue analysis, we input the sinusoidal displacement at the top of the structure. At the bottom, we had fixed restraints, two plane strains quadratic final elements with global size of 0.25 millimeter have been used. And the computational analysis have been done in the framework of the ANSYS software, where strain life approach has been used with consideration of a more mean space correction. And the criterion to obtain the fatigue life was the correct initiation in the weakest point of the analyzed structure. Here we can see first result, the presentation, the relationship between the amplitude strain and the fatigue life. It means number of cycles for correct initiation here on the abscissa axis, and it is clear that the highest resistant against the fatigue failure is actually for tetra anti-chiral structure, while the chiral structure has the lowest resistance against fatigue failure. If the computational results are presented in another diagram where average amplitude force is put at the coordinate axis, in this figure, it is clear that the hexachiral structure can be treated as the most rigid structure if compared to the other analyzed structures. And the last diagram here, the strain energy density is presented in regard to the number of cycles for break initiation. And we can say for this case that the strain energy density is very similar for all analyzed structures. Here we can also see the hysteresis loops. This delta V is actually this strain energy density, and the lowest stiffness, it means the higher flexibility, which leads to the longest fatigue life at a given amplitude stress, is valid for the tetra antichiral structure. And the slope of this hysteresis slope actually presents the Young's modulus for each structure, and here the Young's modulus are presented for all analyzed structures. At the end, some conclusions. So 5 different chiral structures were analyzed in the presented study, and the computational results have shown that trichiral and tetrachiral structures have a positive Poisson ratio. Another 3 structures have a negative Poisson ratio. The endurance curve epsilon A, it means amplitude strain versus fatigue life, show that the tetra antichiral structure possesses the highest resistance against fatigue failure. Another diagram where this amplitude force is presented versus fatigue life show that the hexachiral structure is the most rigid structure compared to the others. And finally, the endurance curve delta V versus this fatigue line show that the strain energy density is very similar for all analyzed structures. However, the tetra antichiral structure is most flexible and therefore possesses the longest fatigue life at a given amplitude strain. And for the research work in the future, so it will be necessary to experimentally test all these structures to confirm the obtained computational results. Thank you for your attention.